So contract manufacturing is one of your biggest relationships when dealing with getting a product to market. It is crucial in your day-to-day development, and it is tantamount to your opinion, or what your client's opinion of you are with the final product, because they're the ones who basically control making it from 1 to 1,000,000 parts. It is important to remember that it is a partnership, but it's also one not based on equity. So it's a dollars and cents situation where you're just doing sales as opposed to actually selling off a chunk of your company to somebody else.
The very first thing you want to consider if you're designing something out of metal is what type of material you're dealing with. So is it aluminum? Is it stainless steel? Is it iron? All of those things will have serious impacts because aluminum melts at 660 degrees Celsius, whereas stainless steel is closer to 1,000 or 1,200. So it's very different styles. Then that will impact your manufacturing method. So the very first one is casting, which works similarly to injection molding, but it'll be a higher temperature and almost no pressure. So the considerations are a little bit different, but they're pretty similar as far as draft angles and taking the part out of the die. You can also cast in different ways, so you could use sand cast, wax, you can use ceramics, a whole bunch of different things. And some of them will have a higher startup or upfront cost or a lower per part cost or the other way around. So it depends how much money you want to invest right away. That'll depend on what you do. The next thing is extrusion. So if you have a fairly long piece that you need to get made, you can pull or push the metal through a die instead of actually casting it. If you want something that's done faster on an assembly line, for example, that's probably easier, but that's a much higher per volume way of manufacturing. And one of the last ones is bending. So you'll start off with something like a plate cut into the shape that you want. You'll bend it in specific places, then you'll probably weld the seams where you need them. And if you're making a metal box or a metal casing or something that's a shell, essentially, that's probably one of the best ways to go. But with bending, you'll get a few issues like hardening, both as a result of the bending and the welding. So you'll have to keep that in mind, and you'll probably need an engineer to take a look at it or take a look at your design. Then with all of these different manufacturing methods, we get different concerns as far as the structural integrity of the part. So with casting, you're likely to get some porosity in your part, which will lead to cracking and different things like that. So if you don't cast it properly, your part will be significantly weaker than what you expect it to be. With extrusion and bending, you'll get hardening of the steel. And this can be a good thing or a bad thing depending on what the application is. So you really need to keep that in mind. Then finally, with metals, there's a lot of post-production stuff you can do. So you could get a polished surface. Usually you do this with a CNC mill. That can be rather expensive though, because it's a fairly slow process. You could also do something like case hardening if you want the steel to be harder if it's in an impact situation. A good example of that is a gear and a gearbox. So with metals, everything is kind of more complicated and more expensive than plastics, obviously, and usually much bigger. So more investment, more VC money will probably be needed to do anything like that. So one of the last things I'm going to talk about here is composites. Specifically carbon fiber and fiberglass, though composites do include other things like pretty much any smart material. So for this, a lot of people like the appeal of a composite, especially carbon fiber. They think it's really cool, but you have to ask yourself, is it really necessary? Do you really need it to be on your part? Because you're going to need a core. So carbon fiber can't be used on its own. It has to wrap around something. So what are you going to make that core out of? Is it going to be foam? Are you going to 3D print the core? Are you going to get that injection molded? What's going to be there holding that carbon fiber together? The next thing is the layer requirements. So carbon fiber is only strong in one direction. If you need your part to be strong in more than one direction, you need different layers, and you need them oriented differently in order to compensate for that. So that's something you really need to keep in mind as well. Then there's the material itself. So some carbon fiber is more expensive, some of it is stronger, some of it is weaker, and there's also a resin. So different resins have different properties. The resin is the glue that holds the carbon fiber to the core. So if your carbon fiber is dealing with anything that gets hot, you need a resin that can resist that, whereas if it's not, you don't need it. So those are all things that make a really big impact on carbon fiber, and they're things that a lot of people don't think about when they go to use it in the first place. Though it is very strong and it is very light, so if you do need it, then it is one way to go.
So, this is something that a lot of people, including myself in the past, have taken for granted, which is getting circuit boards made. So every electrical device, pretty much ever, has a circuit board somewhere in it. Now, how do you actually go about making one, and what are the things to watch out for? So this is something I kind of had to learn the hard way by originally making a few in a project for Cambrian that just didn't work. Then I had to kind of readjust and go through there. So I've got some hands-on experience in this one as well, despite it not really being my formal area. So one of the specific things to consider with a circuit board is the number of layers. So usually this is 2, and by what this means is the amount of places you can put components and or conductive areas. So on a circuit board, you'll commonly be able to flip it over and see parts on both sides. That's called a through-hole or 2-layer board. So basically you can have conductive ink on both sides. Sometimes you can even run the conductive, I'm using ink, but conductive tracing from one side to the other. So we have some examples of this in the shop that, again, I can show you. This is the most common because it gives you the most area, basically double the amount of surface area you've got otherwise. But again, it's a complexity problem. If you really don't need it, no reason to do it. Single layer boards or surface mount, so you've got all your conductive pads on the one side and you can attach everything to that and your bottom is empty. Much, much easier, much, much cheaper, but then you either need more surface area on that one side or you need to go to the 2 layers. So if you're making a really simple component, I definitely recommend 1 layer surface mount board. If you're making something that you have a lot to do but you need to fit it in a small space, then you're going to want to start considering 2-layer boards, and it's actually possible to get more than that, though that's going to be an exponential price increase. So try and keep those in mind, as it's not usually the most intuitive thing and it's not usually straight up mentioned to you. The other thing is mounting holes, and while this sounds obvious, you need a way to attach your circuit board to things. And the reason I point this out is because we have actively worked for projects where they sent us a board that had no mounting holes. So we had to go back to them and be like, yeah, we can't put this in a case because we have no way of holding it in. Like, we can't just glue your board to the plastic. It's kind of not a nice solution. So please, if you are making or getting someone to make a circuit board, please request mounting holes for the sake of everyone who ever designs cases for your products. We will thank you immensely. Now, the other thing, and this was another one of the issues that I encountered the first time I tried to make something, is your trace patterns. And what a trace is, in case you don't know, is on a circuit board, you see, it's usually made of some kind of copper. You see those conductive routing everywhere. So they're usually in kind of like a bronzish, maybe goldish color. I think occasionally you'll see them in silver, though more often than not. Those are basically acting as wires. They're what's carrying your your electrical connectivity, basically, around here, there, and everywhere. There's a reason that all circuit boards tend to move in 45-degree angle steps or less, and that's because if you turn 90 degrees, you're going to probably short circuit or not have a connection. Generally, that results in a bunch of circuit boards that are basically paperweights. And if you send it to a manufacturer, they won't tell you that you're wrong. They'll just give you the one that doesn't work and then say it's your problem. So if you're ever doing circuit board design or someone is doing it for you, that's something you want to watch out for, is make sure you do not exceed 45-degree angles. Not only is it the better solution, but it also tends to look cooler on a circuit board, because let's be honest, those things always look really fancy. Yeah, there's a reason for that. The other thing is your component footprints. And again, I mention this because we've had first-hand experience with this in the shop, which is never order your board unless you have all of your pieces in your hand. Because half the time, the programs used to build a board will have, they'll have a library of the parts already in the software. Not all of them are correct. So we actually had someone attach a timing crystal to their board, and on the design, on the software itself, it fit perfectly in this tiny little spot at the bottom of the board. Then they got the boards made and the parts sent to them at the same time, and when they got the crystal, it was about twice the size of what was showed on the program. And then, so they called the manufacturer. Turns out it was the fault of the people who had made the design program. So now they had essentially a bunch of boards and one component that can't fit on it. I actually think we still have it in the shop, and if we do, I'll show it to you, because we basically have wires coming off the board attached to a piece that just doesn't fit there anymore. Not the best presentation. Try and make sure you have all the parts in your hand before you make things or before you get them ordered. It'll save you a couple headaches along the way, and in the end, that's kind of what this is about. And then finally, your silk screen layer. What that is, that's the actual writing on your circuit board itself. So if you've ever seen like the white writing on a PCB, usually it's just a bunch of squares and things like R1, C1, things like that. Those are to mark where all the components go. Sometimes you'll think you don't need it because you know better. Just put them there. Just trust me, just put them there so that either if you're making it, then you definitely don't have to worry about it. If someone else is making it, you have less instructions to give to them. It just saves the problem. So generally, you basically draw an outline around the component you're putting, and then you label what it is. And then mark that down, usually in some kind of bill of materials, so you know exactly where things go, exactly how they're supposed to fit, and then label the board, usually Rev 0, 0.1, 0.2, all the headaches until you finally get to 1.0. Make sure everything's labeled, make sure everything's marked. It'll save you a million headaches, and ordering printed circuit boards that turn out to be paperweights is expensive. So not something you want to run into and then realize that you can't actually do anything with them. So the next one is product assembly, and this is a part of manufacturing that a lot of people skip, which is the fact that even if you get all your parts, so you've got your injection molded casing, it looks great. You've got your circuit board, it works. You've got whatever other hardware you've ordered. Maybe there's a few lights on there or something like that. Someone has to put it together. Sometimes, in the early days, that someone will probably be you sitting way too late in a garage for however many hours. But that's not going to be what you do forever. And is this something you want to do in-house? So is this something you want to have your own company do? Or is this something you want to outsource? And it is something you can outsource. You can outsource pretty much anything, if I'm honest. So again, big consideration. And another one of these, another one of the points in relation to that is your component sourcing. So I'm going to give you two website names or two company names that hopefully will be a massive help to you if you've never heard of them before. For anything electrical, there's a website called digikey.ca. They have a huge library of electrical components sourced from either one part per order or several thousand per order, and they do next day shipping for no added cost. So if you're trying to build things, and if you're trying to build many things, they're going to be your best friend. I think about half the boxes that come into NORCAT are from DigiKey every day. So just goes to show how important they are even just here. And the next one is McMaster Carr, and that is for other physical hardware. So things like screws, nuts, bolts. You can even get those ribbed like handles for tightening and turning on things. Like any physical hardware you want that you go to add your part and just kind of think, man, I probably don't really need a custom one of these. That's where you'll find it. And they do the same thing as DigiKey. They'll ship very quickly, they'll ship in large volumes, and they'll ship for a reasonable price. Not only that, but they also supply the drawing for everything they offer and the 3D model as well if you're trying to include it in your own part to make sure it works. So if there's any notes you take from this whatsoever, electrical parts, DigiKey, hardware parts, McMaster Carr. It's like, honestly, I think 90% of what we wind up doing as a prototyping company is getting things from them. So trust me. So the next thing is remember that your product has to actually be assembled. And by this, I mean make sure you design it in a way where you can put it together. If you put a screw somewhere where no human can possibly reach it, that's a problem. And yes, it happens. In fact, it happens a few times, and people have made inventions specifically to prevent it from happening. So nuts that act as the other person on a screw. And there are entities where you need two people to put something together because you need one holding the nut, one holding the screw. It gets bad. So remember that someone has to put it together, and even if it's a machine, they do have physical limitations, and they have to actually be able to reach it. So please put them in decent places. Other than that, hardware sourcing, which I just mentioned, DigiKey, McMaster Carr, make sure you have them set up. Make sure it's a company that can supply many. If you're making a product that you want to sell a bunch of, don't get your parts from Canadian Tire. Canadian Tire will run out of stock. They don't really care about you. Get it from McMaster Carr, somewhere like that, that you can place orders for large amounts of volume and get them in a couple days. We have had people come through and, this is the part I'm using to connect my battery to, and it's off the shelf at Walmart, and it was the last one. Not really helpful if you're going to need to make 100 of them. Next one is unexpected and expensive cost. So putting things together is, again, not something most people think of, and it's pretty time consuming. And then tying into that, and this kind of stands out a little, is custom cables. If you're making any kind of electrical product where you have to be moving multiple signals around, Try to avoid any custom cables as much as you can. They take forever to make, they don't feel like you've achieved anything, and they will drive up your cost a ridiculous degree. We have a product that we've helped basically do manufacturing on. There are 14 custom cables in it. Every cable has 5 different separate custom parts that we have to order from DigiKey. Meaning by the time we have all these cables assembled, we've had a box about this big of components that shows up, several hours are spent making these cables, and then we can put the rest of the product together. Massive time sink, massive waste of money. Don't do it if you even vaguely like the person who's putting your thing together. Try and use standard as much as possible, and if not, try and at least keep certain components standard. Like, stick to one connector or one kind of pin or one wire manufacturer. Don't do 10, or 14, not in one product. As best as possible, please avoid that.
So the first point kind of ties back to everything we talked about. You have to first identify what the appropriate manufacturing method is for what you're doing. Are you making it out of plastic? Are you making it out of metal? Is it a PCB? How do those things come together? So your tolerances will play a big factor here. Different manufacturing methods will give you different tolerances. Some things will be much more small scale, so it might be 1 micron, or it might be ½ an inch tolerance. It makes a huge difference. The second thing after that is choosing a manufacturer. And I'm saying that as one point, but that is an extremely large part of the process. So picking who you're going to deal with. There are a lot of factors there. Just to list a few, we have location, the experience of the manufacturer. So you want to see their portfolio. You want to see what they've done in the past, because you want to pick someone who's actually done this before, preferably. If it's their first crack at it, it might not go as smoothly. Then you'll want to see what the quality of the output is. So, I mean, this will play a huge part in your quality control and quality assurance later on. You want people to buy a product that looks good, that feels good. If it's not to the level that you want it, you're obviously not going to want to buy it from them. Then final thing is the cost. So when you're comparing different contract manufacturers, you really have to decide if you're going to cut a little bit of the quality for a much better cost, or are you going to, add that money in there to get a better product out of it. So then the kind of last thing here is what Daryl was talking about with getting the different pieces that go together. So when you have a product, you need all these things to come together, and you need to consider stock, you need to consider scheduling. So are all these things going to make it to you on time? Are you going to have everything you need to make your part? Or is one thing going to hold you back? Are you going to be missing one component that means that you can't put any of it together? So when you're thinking about this, you really have to keep track of where everything is and when it's going to come in. So injection molding specifically, it's one of the most common contract manufacturing processes. It has a very high upfront cost. So like I said, dies can cost from $10,000 to $100,000. And they can be made out of aluminum or stainless steel. Aluminum, typically, you'll get about 10,000 parts from. After that, they'll have to make it again. So often these dies are CNC'd, and that's where that cost comes from, is making those. But the parts themselves will cost pennies a piece. So you'll spend 15, 20 grand on the die, but you'll spend 5 cents on each part. So that's where you have to consider that 3D prototyping. Are you making 100 of them? Are you making 1,000? Are you making 100,000? And it's kind of one of those math problems from grade 9 with the 2 lines and where they cross. You have to kind of go through that. So a local example of injection molding is North Bay Plastics. They will do a lot of more complicated projects. They won't really consider you unless it's an automated process and a fairly high scale thing, but they do injection molding locally. So we do have places that do this around here. The second thing I'll talk about is metalworking. So again, the processes that you can do: casting, extruding, bending, welding. I won't go through them again. But with metals, you also have the post-production, so the CNC milling to get that polished surface. You can electrocoat, so you could have a steel part, and then you could coat it in something like a stainless or a chrome or whatever to get an aesthetic or an actual engineering type added feature to it. So it could be conductive, it could be insulated, it could be a lot of different things. The case hardening, again, if you wanted to make it stronger or more resistant to impact. And a local example of that is Sudbury Stainless, so they'll do a lot of your stainless steel type stuff, whether that's CNCing or casting or whatever else. So all these things, I mean, we think of contract manufacturing and our heads go directly to China, they go directly to the people who send us emails 4 times a week saying, we can do this for you. There are places to do it around here if you want it. And the benefit to that is that you can go see their shops, you can go see their equipment, you can see the things they've done. And at the end of the day, it's probably a better relationship with your company. So seriously consider those when you're going through this process.
So in this case, you have a high low volume cost, and what I mean by this is if you order 1 circuit board, you're looking at upwards of $100 to $200 per board, which is a huge amount for what you're actually getting. Keep in mind that actually that is a unpopulated board. So that's a board with literally none of the components on it, just the traces as to where they actually go. But it's a really low high volume cost. So once you're starting to sell a lot of your parts and you're ordering PCBs in more of like 1,000 or 10,000, suddenly the cost of those boards start dropping to $1, under $1, under a couple cents. Like they start really, really, really plummeting. So this is why I'm saying you really want to get that board right or as close to right as possible sooner, so you don't have those several $100 for 1 board orders and you can skip straight to the cheap ones. There are actually some things that I want to point out in here you can take advantage of. A lot of PCB suppliers offer a deal where they give you basically a board of a certain size, and then you get as many as your circuit boards can fit in that size as possible for 1 price. So if you have a very tiny board, you can actually find someone who will offer you maybe square foot of printed circuit board and say your circuit board is maybe 2 square inches. That's a lot of boards for a pretty cheap price. And that's regardless of how many you're ordering. So look for those kind of deals, especially if you're doing something smaller. They'll really, really help you out. They'll really help you save cost. If you just send someone a design, say, I need these, you're going to get prices back of 100, 200. I think we've seen upwards of 500 for one particular company. So that's something you want to consider. There's a bunch of companies that'll do this locally. Crest Circuits is a good example. I think they're out of Markham by Toronto. I've also used one out of Florida, and there's a couple out of Alberta that are quite good as well. Shop around, they're everywhere. Compare prices, compare the deals, especially those you get a certain amount in the size space things. And then when you want to go large, then you can start kind of hunting for better deals there. So the other thing to consider is so whether or not your board is populated. What this means is, are the components on it? And this is definitely something you can do. You can buy your board from companies that will get all your components, will put all your components on the board and then send it to you that way. There is a hefty, hefty markup on that service. So if that's something you can do in-house, do so. But if it's not, I don't recommend trying just as a first time. Soldering is not too bad when you're working with a lot of space or prototyping boards. Soldering on a small circuit board is nothing short of a nightmare. You can do this in other ways, and what I'd recommend is small wave soldering machines. What this is basically you put all the components where they're supposed to go, you put the entire thing with all the components in it in basically an oven, and it does all the soldering for you in one shot. I have also seen this work out where there was a small fire before, so read the instructions. But still, you can do things much cheaper that way, and those little wave solder machines are pretty cheap. I've actually even seen people do it with like one of those Canadian Tire heat guns. They've populated their entire board by putting all their components down with a conductive paste, and then just going over the entire thing with basically the equivalent of a hairdryer. That actually works, but not ideal in the long run. Still saves you that cost of getting someone to do it for you. If you're ordering thousands of boards, you may want to offset that cost. Companies that'll do population, I can't think of too many offhand. A lot of the circuit boards people will offer it. I know in the NORCAT building soon there's going to be a pick and place machine as well as one through the Fort Discovery Lab. What that is a machine that'll actually basically use a little vacuum hand, pick up your components, put it where it's supposed to go on the board, and then solder it itself. So basically an automated process like the big companies offer, except meant for more small scale. So if that's something you're getting into, hopefully we'll be able to help you in the very, very near future. And the other thing is, again, this is product assembly, and PCB population is the biggest one there. You don't want to assemble your PCB by hand. You want to try and do wave soldering. You want to try and do pick and place. If you cannot outsource it, that'd be better, but just by hand is not a good call. We've had to do it a couple times. Even simple boards are slow and potentially nightmarish. It's very easy to ruin an entire board with one little drop of solder. The other thing is your product something that is hand assembled or something you can use on an assembly line? A lot of clothing, for example, or wearable products, you don't have much of a choice other than hand assembly, which is pretty expensive because it's basically just straight labor cost. Something more mechanical, something that's optimized for it, you can get away with assembly lines. Again, that's usually high volume, but it's something to consider when you're making your product. How is this going to be put together? Who is putting this together, and how can I make this better for them? Because in the end, if it's better and faster for them, it's cheaper for you. So that, it's ease of assembly, and then there's outsourced versus in-house. If it's something fairly simple you can put together, especially as a small company, it'll probably be you in a garage. Otherwise, so you can start looking for more outsourced companies or hiring people to do it yourself, or themselves. And then finally, packaging. So this is something that actually is large-scale manufacturing, but a lot of people don't consider, which is how is your box going to be packaged? First thing to consider here is this off the shelf or direct to consumer? So is this something that you want to be sitting on a Walmart, Canadian Tire shelf, catching people's attention? Or is this something that people are going to be buying online and you're going to send straight to them? Basically, that comes down to a difference of how pretty do you need it to be. So I've ordered things before that just come in a straight brown box and a bunch of bubble wrap, and that's fine because it's not sitting on a shelf somewhere and I don't have to worry about it. But if it is, then you need to do the more glossy boxes or vacuum packaged, those impossible to open plastic things. Yeah. So those are vacuum form packages. Those are something that actually is a large scale manufacturing problem because you need a die, you need a vacuum forming table. They're not cheap to do, but they get attention because all you need is a cardboard insert in the middle to brand your product. Good thing to note there is you can get things like pre-made packaging. So standard size boxes or standard size vacuum form that'll fit a certain size of products, and the only thing you need to do is supply the rest of the inlay. It's a pretty cheap way to get around the large scale manufacturing side of things, especially in the early days. Keep it in mind. And then finally, there's custom inlays. So if you've ever opened a product, pulled out a big sheet of styrofoam, and all of the components are perfectly fit into their own areas, that styrofoam is something that also has to be custom made. So even though it's something you pull apart, pull your product out of, it makes a giant mess and the kids break it apart, it is something you actually need to commit money to making and getting sourced. So something to consider when you're making your product. How do you want this to look when someone opens it? And really, how far is necessary for you to go? So finally, in your, finally, you're going to want to consider intellectual property in that relationship.
So for a lot of people, they spend years and years working up to starting a company, to going out to find your contract manufacturer. And when you finally do, you have that fear that they're just going to take it and rip you off. They're going to make their own copy of it. They're going to sell it to somebody else. And that's where these three important documents come into play. So the first one is patents. By protecting your idea as a novel idea through the government, you have a little bit more protection against people knocking you off or making an exact duplicate to it, by proving that you have the rights to it. Now, the other concern is that they're going to make a product very similar to yours. Doesn't technically break your patent, but it does everything yours does and maybe a little bit better because they can see what the competition is. And that's where non-disclosure agreements come in. So the company you're working for is not going to go and tell everybody about your idea. They're not going to try and sell it to the next highest bidder. They're not going to try and make a duplicate of it because they have it in writing that it's illegal for them to do so. The big concern with both non-disclosures and non-competes, it is your responsibility to bring it to the company that is working for you. Some companies, most companies that participate in the market ethically may provide you with one, but at the end of the day, if you get screwed, it would be because you didn't provide it to them. You didn't ask them to sign the document. You didn't ask them what their protocol for these situations are. And so it's something you have to investigate and something you have to look at. And it's something that is a lot easier to work with a company when you can go down the street, knock on their door and say, hey, how do you protect me? How do you protect my product? And then the last one is non-compete agreements. And so basically what this means is you've worked with the manufacturer, they've made your product, They haven't taken it to somebody else. They've followed every regulation, but now your contract's done. And they're going to pick up a contract from your next leading competitor because they've worked with your product and they know everything about the sector. And so by signing a non-compete agreement, you have a certain window in which this company won't go and get hired by your direct competition, won't try and put you out of business in a sense. Generally, these agreements will go for a certain time frame or until your product comes to market so that you have a chance to hit the ground running. And generally, they're pretty distinct. So if you were designing a cap lamp for the mining industry, you can't say that this company is not going to work with anybody in mining. That's a little bit unrealistic. But to say that they won't design lighting sources for a mining environment is a perfectly reasonable concern.
So once you have a product, once you're looking at putting it on the shelf, once it's good to go, you get to this stage, which is testing and certification. It's distinctly different than the testing we had before. That's more like you build a prototype, you see what's wrong with it, you fix that. This is an official certification that I'm talking about. So one of the first ones is environmental testing and ingress protection. So ingress protection, or IP, you may have seen it on phone commercials, like the Sony Xperia. There's a few of them now that have IP67 certification. And what that means is you can drop your phone in the water up to 1 meter deep for 30 minutes. And different IP certifications will mean different things. So it's dust-proof and waterproof. That's what the two numbers mean. So this is something you can actually self-certify, believe it or not. But it's something that's good to have, especially if you have gasketing in your product or if you have electronics. You want it to be able to withstand some dust and some water, depending on what the environment is. The next thing is an engineering stamp. So this is a professional engineer that stamps your design. It isn't necessary all the time, but what it does give you is essentially a layer of protection for liability. So if an engineer stamps your document, he is taking the responsibility, the liability for that. He is saying that your design is good, that it's safe, that it withstands all that it needs to. So if it's something that deals with the safeguarding of life or property, you definitely want a stamp on there. It'll also mean that your product will comply with all the ASTM and all the ASME codes. So that's the American Society of Mechanical Engineers and Testing and Materials. And they have different codes for different products in different situations. So on one end of the scale, you have pressure vessels that have to not explode, and you need a specific stamp, and it's called the U stamp. You need a bunch of certifications. It has to follow a specific code. And on the other end of it, it's just small things that won't light on fire if you plug them in. Like, it goes from common sense to way up there in terms of safety. So the next thing is electromagnetic certification. This is, again, mostly with electronics. Your electronics can only output certain frequencies, and they have to be able to deal with certain frequencies being dealt to them. So in an EMC chamber, which we actually have in the shop and we can show you, your board can be tested as far as if it can deal with other frequencies that are around it. So your Wi-Fi, your data for your phone, that's all at certain frequencies. And if your board gets impacted by those frequencies, it's essentially useless, right? Then on the other side of it is if your board is outputting something. If you're walking into a hospital or if you're in a mine, it can't output at frequencies that will disrupt the other equipment in there. So you have to get that checked. The last thing is abiding to applicable codes and standards. This is something that if you're seriously considering in your product, you'll want an engineer to take a look at it. ASTM and ASME are the big ones, but I mean there are different codes and different standards for every different product you could think of. So testing and certification is something that you need to do, especially if you're looking at like a consumer product. It's really important.
All right, so last slide. I know Haley's coming after me. Is basically volume production, moving from low numbers to high numbers. This is pretty obvious. We've gone over it a couple times. Basically, there's going to be two main costs you really want to look at, and it is that grade 9 math problem that we all were saying, when will I ever use this? Yeah, one of the answers. How much is it going to cost you upfront to get this going? Is it going to cost you $10,000 for a die, $20,000, $100,000? What is that big first number? And then what's the per part number? So ideally what you want there is kind of, well, I mean as low as possible on both, but ideally what you want is for that second number to be the one that's most important to you. So if it's the high upfront cost, but then after that your parts only cost a matter of cents, that profit margin will take a significantly shorter time to, give you the return from that big upfront investment. That's why injection molding is so popular. It's a big upfront cost, but the actual components are cheap. Next is low volume versus high volume. Low volume is always more expensive. High volume, however, is a larger chunk of money. So high volume will give you less of a profit margin. Low volume will give you less of a profit margin. High volume will give you more, but are you realistically going to make those? And that's why we have in here realistic quantity expectations. So those numbers you used in your business plan that, to get funding and to look like you're going to do really well, yeah, don't use those. Use the real ones. And I'm sorry for the people at NORCAT who've said certain things about business plans, but use real numbers. You don't want to have a million parts that are never going to sell. You want to make sure that you have the right amount to not run out, but not to be an excessive amount of things sitting on shelves just being money that you spent and never got back. So that's where schedule reliability and maintaining stock comes in. You want to have a certain amount of stock to deal with sudden increases, but you don't want to have too much to basically just have burnt away money. So that's your scheduling. You want to make sure things come in on time to never really run out. So trying to have those realistic numbers and plan accordingly is going to be really, really important in your long run. Ideally, by the time you have those kind of problems, you're already good. So hopefully you all get to that point. And finally, there's quality assurance. I'm sorry. I thought it was the last one.
Just do it quick. Basically, you want to make sure that you're giving the same product to the client when you're making 1,000 of them as when you're making 1,000,000 of them. And so a couple of ways to allow for this is oversight, having some ability to control what the manufacturer does, making sure they don't then outsource their work to less competent people or that they choose lesser materials. Also to ensure for this, you can take a sampling of the parts that are made and make sure that, say, 1 in 1,000 meets the quality that you want. This can be done by a person sitting there picking them up, looking at them, or it can be automated. Usually these involve testing either destructive or non-destructive, and that's just basically seeing if it'll work in the way that you want it to work. And then documentation, so being able to go back to your manufacturer and say, you gave me this list of what you're going to do to make sure that I get the best product, and you skipped steps 3, 5, and 8. And so they're just ways to protect yourself when you are making 1,000,000 of them, and you're a pretty big contract at that point, so it's fair to expect them to bend over backwards for you.
So finally, if you have any questions, by all means, please ask us. And if you're interested, and we have enough time, we can bring you through the Fortin Discovery Lab to show you some examples of these as well. And that's kind of at your own discretion. So we've got no problem showing you around. And thank you.